Hello, this is Jennifer Martinez. In this video, we're going to talk about the characterizations of invertible matrices by looking at the following theorem, the invertible matrix theorem. As you can see, it has many parts, but it's a very powerful theorem as it contains many concepts that we learned in Chapter 1, and it ties them all together with invertible matrices. For instance, it connects the concepts of the linear independence of the columns of a matrix with the existence of the solutions of that matrix equation and the existence of the inverse of that matrix. However, it only applies to square matrices. I really want to emphasize this. For example, if the columns of a 4x3 matrix, that means 4 rows, 3 columns, are linearly independent, we cannot use the invertible matrix theorem. As you can see on the first line, it says let A be a square n by n matrix. And then the following statements are equivalent. And part A is invertible. So A is an invertible matrix is equivalent to all these other parts. And yes, we are going to prove this theorem. So let's go ahead and do that. So I'm going to start by just looking at D is equivalent to E, which is equivalent to F, which we actually have already proved in section 1.9. Let me make this smaller so you can see the actual theorem. So the equation AX equals 0 has only the trivial solution, is equivalent to the columns of A form linearly independent sets. With F, the linear transformation is 1-to-1. We saw all those three from chapter 1. The other ones we've already proven is G, H, and I, and they're listed here. If you look at G, H, and I, the equation AX equals B at least has one solution for each B in Rn. The columns of A span Rn, and the linear transformation A to AX maps Rn onto Rn. We know all three of those are equivalent. So what we need to do is just do the following. If we can imply A, let me just check these off here. There's A. That implies J, which implies D, is equivalent to D, or implies D, which implies C, which implies B, which goes back to A. We will prove that all those are equivalent. And since we have D, we'll automatically have E and F. But we do have some missing there. So then we're going to go back to A and then prove K and then G. And then we know again from the left side here that that automatically gives us H and I. And we have proved most everything except for L. L, you can find a proof from the last section that A is invertible, implies or is equivalent to the transpose being invertible. So let's go ahead and start. I'm going to start with A implies J. So I'm going to let A be an invertible matrix, which is what part A is. And then we just have this by the definition. Because by the definition of an invertible matrix is there exists an n by n matrix C, such that CA equals I, which is exactly what J is. So that is done. So now let's look at J implies D. So let's suppose J. Suppose CA equals I. And let X be an Rn where AX equals 0. What do we want to prove? D, which is that equation only has a trivial solution. So what I'm going to do here is I'm going to multiply both sides of this equation by C on the left side. So now we can say CA, that particular C that made this I, that's just 0, which, by the way, that means that, oops, ran out of room, x equals 0. So therefore, x only has the trivial solution, which is what D was. So that is that one. So far A implies J, J implies D, so now I'm on D implies C. So now suppose A is an n by n matrix with AX equaling 0 only having the trivial solution, which is what D was. Or it's right there. So then there are no free variables in this equation, so A has n pivot columns, which, by the way, is what C is. Let's go look at C again. A has n pivot columns. So that proves that. So if A is a square matrix with n pivot columns, then the pivots must lie on the diagonal. So the reduced echelon form of A is I. So if we look back up here to C, yes, that was C implies B. So if we look at C, C was A has n pivot columns, and B was A is row equivalent to the n by n identity matrix, which is exactly what that says. So in other words, A is row equivalent to the n by n identity matrix. So finally, we need to get to B implies A, and then we are done. But Theorem 7 from the last video states just this. It states that an n by n matrix A is invertible if and only if A is row equivalent to I. So A is only equivalent, A is row equivalent to I was just B. If we go back and look at that. And therefore A is an invertible matrix. So we've just completed the loop. So now we have that each of these statements are equivalent. By the way, the proof of this is in the book, and I think listed on the last video. So finally, all we need to prove are these A implies K implies G, the second circle. So what I did here is I decided to recopy the theorem and just the little circle that we need to still prove, so I don't have to scroll back and forth each time. So let's go for A implies K. So let's let A be an invertible n by n matrix. And we know K just by the definition. We know by definition of an invertible matrix that there is a n by n matrix D, we can call it, such that AD equals I, since we've already used the C. So we just know A implies K is by definition. So now let's go for K implies G. So suppose we have K, that AD equals I, and let's let B be an Rn. What we're going to do is something a little weird. We're just going to look at the equation ADB. It's like an AX. That's going to be my X. So I'm going to switch this to ADB, which we know is I, which we know is B. So what does that tell us? That tells us that we found an X. It tells us that X, being this DB, satisfies AX equals B, because if I put this in here, I get this line above. This proves that the equation ax equals b has a solution for b and Rn. And if you look at G, that's exactly what it says. The equation AXB has at least one solution. I found it for each B and Rn. So that's K implies G. So now we just need G implies A. And then we're going to finish our loop. Suppose AX equals B has at least one solution for each B and Rn, which is exactly what G stated up here. So by theorem 4, back in chapter 1, A has a pivot in every row. Since A is an n by n matrix, there are n pivots. I even copied the proof of theorem 4 from chapter 1. The proof is a little bit more difficult. But there is, you can look in the book in after chapter 1, after theorem 4, and the proof is right there. And what does it say? Part A, that each of these statements are equivalent. I know we have an n by n matrix, but in our case it's an n by n. For each B and Rn, in our case, the equation has a solution. We have that. And A has a pivot position in every row. Just part D. So that tells us that A is invertible. Since there's n pivots, we know that A is row equivalent to I. And again, by theorem 7 from the last video, A is invertible if and only if A is row equivalent to I. We made that same argument. So we now have completed our loop. We did A implies K, K implies G, G implies A. And we have proved theorem 8, the invertible matrix theorem. The last part, L, it's on its own. And if you look at the last section, like I said earlier in the video, that last A is invertible if and only if A transpose is invertible was proved in the last section. So that is the only separate one. So now let's look at an example. Let's look at example 1. It says use the invertible matrix theorem to decide if A is invertible. So let's copy or look at the matrix theorem, invertible matrix theorem. I copied it down below here so we can look at it. And what the book decided to do is C, showing that A has n pivot positions. So they row reduced it, and they got the 2 zeros underneath that first pivot and a 0 underneath that second pivot, and realized there's 3 pivots. And it's a 3 by 3 matrix, so therefore it has to be invertible. But you did not have to do it this way. There's many ways that you could see if this is invertible. For instance, let's do part D. Let's show that AX equals 0 only has the trivial solution. So let's look at AX equals 0. So that becomes this matrix here, which we can reduce that to the same matrix that they had, except for with zeros on the right. Therefore, this only has the trivial solution, hence invertible. So with this theorem, you have many choices. So let's do a practice problem. Determine if this A is invertible. Well, it's not. Why not? Because if I look at these columns, I realize that they're multiples of each other. Like for instance, the second column is 3/2 times the first column, and the third column is 2 times the first column. So therefore, they're dependent, which means they are not linearly independent. P, if and only if Q, is the same as saying not Q, if and only if not P. So we have it's not independent, so therefore it's not invertible. Here's their solution.